I'm going to walk you through a quick example for the CacheLab. In this example, let's assume we have 16-bit addresses, but the real CacheLab has 64-bit addresses. So our addresses have this format with 16 bits each, and we need to divide those up between the set bits, the tag, and the block offset. In this example, let's use B is going to be 4, S will be 4, and then E will be 2. So in this case, we start on the right hand side, and we have 4 bits for B is 4, and then the next 4 bits here will be for S is 4, and then the tag bits is the whole address minus S minus B is going to be the remaining bits. In this case, that will be 8 bits. So what we need to do is build our cache. And so the main thing we're interested here is S. There's 4 bits for the set. And so we need 2 to the S is 2 to the 4 is 16 cache sets, and then of 2 lines each. So we can build this, and this will be addresses 0 through 2 to the S equals minus 1 equals 15. One too many. All right, so, and we could write the addresses in binary as well. Etc. And so these correspond to the 4 bits for our set address up here. Now each one of these, we need to keep track of the tag, and we need 2 sets. So we're going to have 2 sets of cache line per address. Etc. If we were building a real cache, we would need to hold 2 to the 4 bytes inside of these. But in this case, we don't actually need to store the data, so we don't need to actually construct storage for those bytes. So let's look at an example of how this would be used. So say we have some memory access of 3E25. So all of this is in hexadecimal, and because I've constructed this example on purpose, each of these hexadecimal digits corresponds to 4 bits, which happens to be the same size as our block offset and our set size. So I can do this actually quite easily then, is I can know this part is going to be the tag, this part is going to be the set, and this one will be the block. So what I need to do then is basically separate out these 2 parts. Okay, so and this needs to work regardless of how big your block offset is. So what I want to do is I want to essentially isolate these bits here. So here's where your data lab comes in handy. So you need to shift this whole thing right by B bits, and then mask off S bits to isolate this. So we want to get set 2 in this case, and we're going to then use the remaining bits over here as the tag to store something. So if I come up here and find my set 2, here's my set 2. I'm going to be storing something here, and the tag will be 3E, and let's call this time 1. and we could say this is a valid cache, that there's something in there. So it's up to you to decide how you're storing these things, but the main thing is I need to store the tag in here, and I need to know it's valid, and I probably need to know the timestamp, or I need to know some ordering because I need to know when I'm going to evict things. So say I have some other address here, so at time 2 I try to do 0x5225. Now in this case we have the same set, and I'm going to store that in the next cache line because I had 2 cache lines. So this will be tag 52, and then I'm going to say this is time 2. All right, so now I'm going to time 3. I have another memory access, 0x2721. So if I try to do this one here, I also have set 2. So I go to set 2. There's already 2 things in the cache that are valid, so I need to evict one, and the one that I'm going to evict is going to be the older one, the one that's least recently used. So you could have stored either the timestamps in here, and in this case I'm using timestamps as just the order of things in my trace file, or I could have stored this as some sort of priority queue where I could rearrange these lines. So in this case I'm going to evict this guy here. He'll go away, and I'm going to then store the 27, and now I'm at time 3 for that one. All right. So let's do time another access here, and I'm going to access 0x5221. Okay. So again, I'm still in set 2, and so what I'm trying to do here actually is, now that I'm in set 2, I'm looking for something. I'm going to scan all of the tags in set 2 and see if I have a match for the tag in this one here. Okay, so the tag I'm looking for is 52, and here I have no match, and then I can come over here and I do see a match. So 52, so that tells me I have a hit. Okay, so I have a hit, and basically I can ignore the block offset because I didn't actually have to store the data, but each one of these cache lines would have stored 2 to the 4 bytes, which would be 16 bytes. So basically this last address here we can ignore as if it doesn't exist, okay, except that we need to shift over in order to isolate the set address. Hopefully that makes things a little bit clearer. In all these cases I was reusing set 2 on purpose, and we'll notice here that the tag is really a prefix of the address, right? So the set determines which one we're going to access from the cache that we've created. We need to search across all possible set lines to see if we have a tag match, and if we have a tag match, then we have a cache hit. If we have a tag, if we don't find a matching tag, we have a cache miss, and if there's things that we need to evict, we need to evict the one that is the oldest.